Aging, as it turns out, isn't just a number, it's a texture, a tone, and a microscopic pattern written across your skin. Beneath the surface of crow's feet and sunspots lies a story told by cells, especially the quiet but influential senescent fibroblasts. These cells, which lose the ability to divide and begin secreting a mess of inflammatory and tissue-altering factors, are increasingly being recognized not only as contributors to aging skin, but as living timestamps of the body's true biological age. What if we could read those patterns, those cellular signatures, and use them as a kind of skin-based clock to measure how fast someone is really aging, inside and out? That's the premise behind a growing scientific movement to turn senescent cell subtypes in the skin into biomarkers of biological age. Unlike chronological age, which is just the tally of birthdays, biological age reflects the actual condition of your tissues, your disease risk, and your physiological resilience. And the skin, being both visible and accessible, is a perfect testing ground for non-invasive diagnostics. We already use skin to check hydration, circulation, and immune response. Why not use it to read aging itself? The key lies in recognizing that not all senescent cells in the skin are equal. Fibroblasts, which make up the bulk of the dermis and produce collagen and extracellular matrix, are particularly prone to entering senescence with UV exposure, oxidative stress, or repeated injury. But they don't all behave the same way once they do. Some produce inflammatory factors that drive visible aging and chronic disease risk. Others become metabolically sluggish, altering how the skin responds to injury or inflammation. Some even begin expressing markers linked to systemic diseases like diabetes or cardiovascular dysfunction. By classifying these senescent subtypes through morphology, gene expression, secretory profile, or metabolic activity, researchers are beginning to build a library of skin aging signatures. These can be used to estimate not just how old your skin is, but how your body's biological systems are functioning more broadly. For example, a skin sample might show a high proportion of P16-INK 4A plus fibroblasts with a pro-inflammatory SESB, suggesting accelerated aging and a higher risk for metabolic disease. Another might reveal a quieter, less harmful subtype more consistent with chronological age. This opens up the tantalizing possibility of skin-based diagnostics that go far beyond aesthetics. Machine learning and high-throughput imaging are accelerating this shift. With AI, researchers can scan thousands of skin cells and detect patterns that would be invisible to the naked eye, slight changes in nuclear size, cytoplasmic granularity, or even spatial clustering of different senescent cell types. Algorithms trained on age-diverse skin samples can begin to predict biological age based on these features, outperforming traditional blood markers or subjective clinical scoring. And because the skin renews regularly, these changes are dynamic, offering a real-time snapshot of how interventions like diet, stress reduction, or medication may be affecting your aging trajectory. There's also interest in how skin-based senescence profiling could serve as an early warning system for disease onset. Studies are now linking certain fibroblast senescence patterns to systemic conditions. For instance, increased SASB expression in dermal fibroblasts may correlate with insulin resistance, cardiovascular inflammation, or immune dysregulation. If confirmed in larger studies, this means a skin biopsy, or even a high-resolution scan, could one day predict chronic disease risk before symptoms emerge. What's especially compelling is the potential for personalized anti-aging strategies. If we know which types of senescent cells are dominating your skin, treatments could be tailored accordingly. Someone with mostly inflammatory senescent fibroblasts might benefit from xenomorphics or anti-inflammatory serums. Another person with matrix-degrading subtypes could be directed toward therapies that restore structural proteins or activate regenerative pathways. It's not just about looking younger. It's about using the skin as a readable, modifiable map of your inner health. Of course, there are challenges. Senescent cell detection in humans is still messy. Current biomarkers like SASSCAL or P16-INK4A are not fully specific, and skin is influenced by external factors like UV light, pollution, and lifestyle. But advances in multiplex imaging, spatial transcriptomics, and AI-based cell classification are bringing a level of precision that was unthinkable just a few years ago. In the near future, your skin may no longer be just a cosmetic canvas. It could be your most informative health report, a living clock that ticks in sync with your internal biology. Instead of asking how old you look, we'll be asking what your skin knows. And if senescent fibroblasts are the timekeepers, it's time we learn to read their signals.